Hi all, and welcome to C++ for Java Contest Programmers, Part 1. So there's been a lot of interest in the team recently in C++. So right up front, I'm going to talk about whether or not you should switch to C++. This talk is not a mandate to switch from the coaches. This is just us responding to you all being interested in C++ due to some stuff that's happened in recent contests. And the fact that everybody knows that C++ is becoming more and more the language of choice for competitive programming. We need to do this strategically, though. We can't just switch because it's the thing to do right now. So in fall, if you don't know C++ and you're just starting out, and this is true on either JV or varsity, you should still be concentrating on algorithms, concentrate on solving problems. Those skills translate in either language, and it's better to not be trying to learn two things at once if you're also like trying to come up to speed on C++ when you already know Java. You're just going to split your attention. Java should be fine for regionals and Mercer. The time bounds being really, really tight is more of a NAC World Finals thing. So after the regionals or Mercer timeframe, you should work with your team's coach and talk about whether it's a good idea to switch, and that's going to depend on a lot of things like the makeup of your team and what everybody knows and so on. This talk is going to be archived online, so even though we're talking about this now, if you don't switch until fall, if you don't switch until spring, or whenever you decide is a good idea to do this, you'll still be able to go review this content. So don't worry about the fact that you won't be able to go back and listen to this again. The intent here is not to teach you general C++. That would take a semester, not a couple of half-hour talks. We're going to go over a very specific subset of C++ that's useful in contests, and also that is the easiest ways to write C++ that doesn't have bugs. Everybody has heard that in C and C++ there are many easy ways to shoot yourself in the foot, and that's true. And we're going to try to just avoid those features, and it turns out that for doing contest programming, you can pretty much just pretend those things don't exist and not use them. So we're going to go deep on a few things that are useful for contests, and we're going to ignore a whole bunch of other stuff that you just don't need to know right now. And that's going to be enough for you to do most contest problems well. The features I was alluding to are pointers and memory allocation for the most part. Pointers are just a way of having an address to a piece of memory, and it's totally unchecked. And if it's wrong, you're just smashing random memory. Memory allocation is explicitly asking for a number of bytes. And again, that's problematic because you have to go figure out how many bytes you need. You have to make sure, even if you're using new, like in Java, where you are creating an instance of a class, if you knew something, unlike Java, C++ is not garbage collected. So if you go newing stuff all over the place, it's not going to get cleaned up for you. This isn't as much of a problem in contests because typically we allocate a few very big things, but still in general there are better ways of doing this where you can guarantee that the compiler is going to clean up after you. And we'll talk about that when we get to the containers section. So along with every other programming talk in the world, we're going to start with Hello World. And there's a few basic things here. This is a small program, but there's a lot of the flavor of C++ in this. So we're going to go over this line by line. The first thing I want you to notice is pound include. So anything with pound as the first character is a directive to the compiler, not actually code to compile. So pound include here is telling the compiler to include another file when it's compiling this file. And in this case, the file we're including is IOStream. So this is the equivalent, not quite, but you can think of it as the equivalent of import in Java. In this case, we're bringing in IOStream IO stream contains all of the things you need to do standard IO, input and output to the console. And then we have main. So again, there are some differences from Java here. First of all, you can see the declaration is pretty much like a Java method declaration. We're returning an integer, but main is not a member of any class. In C++, it turns out you can actually have just plain old functions that are not methods of a class and have no this pointer. And unlike Java, where main is a static member of some class, and then that class is the main class of your program, in C++, the entry point is just called main. And it can take command line arguments. I'm not showing you how to do that because we never do that in contest problems, but if you did, there are arguments to main where they would get passed in. And the other thing to notice is that we're returning an int here, but we're not returning anything. So in C++, you do have to return something from a function that has a non-void return type. It turns out, though, that main is special, and if you don't return anything, it implicitly returns 0. And this isn't just a, trivia type of thing. This is actually important. Because if you return early out of main, you have to return something because you're returning an int, and what you return had better be 0. And the reason for that is that value actually gets returned to the operating system, and 0 means success, and any other value than 0 means failure, and by convention, like what that value is means how the program failed in some way. So judging systems, actually a lot of them, including Sparta, look at that value, and if they see a non-zero return code from the program, they assume the program failed. So if you say early out for some reason and return 1, you're probably going to get wrong answer and not going to know why. So important safety tip, if you return early out of main, always return 0. The next thing we're going to talk about is namespacing. And namespaces are nothing more. You can think of them as just a way of collecting together a bunch of related functionality and having putting a prefix on it to keep the name from colliding with anything else. So there's a namespace called the global namespace, and the global namespace is everything that's not qualified. So main is in the global namespace. If you declare a variable in main, you could declare a variable called cout as an integer, and it would not collide with cout, at least not as we have the program right now, because cout is in the namespace standard, and the cout you declare as a variable is not. And pretty much everything that we're going to talk about, the only thing that's not is math functions, like square root, log, blah, blah. Those are all just functions. But pretty much anything we're going to use other than that is in the standard namespace and has to be qualified that it's in the standard namespace when you use it. And we'll show us actually a way around that to make things easier in the next slide. The other thing I want you to notice is this weird use of what you're probably used to thinking of as the shift operator, left shift or right shift, if you're dealing with bits. C++ overloads that for I/O. Some people think this is a great idea. Some people think this is a horrible idea, but this is what they did. So this cout is what's called a stream. And since it's an output stream, it takes data. So an easy way to remember, so you actually put these in the other direction if you're doing input. The arrows point in the direction of data flow. So here, hello world is flowing into cout, so cout is going to print it. The return value of running the stream output operator on cout and hello world is cout again, which means you can chain these things together. And that's what we're doing here. We're chaining, first we're outputting hello world, and then on top of that, we're chaining ENDL. Again, it's in STD. And what ENDL is basically \n. It's new line. ENDL is the proper way of putting a new line because there are systems that don't use \n. Anything we're doing, you could just say hello world \n, but this shows you how chaining streaming together works, so I wanted this for the example. Okay, so how do we avoid having to litter our code with std : all over the place? Some people will tell you that you should just train yourself to type std : and if that works for you, that's fine. I mean, it's only 5 characters, and once you're used to typing it, you can type it really fast. But if you want to do a shortcut, this is how you would do it. So there's a keyword called using, and we'll talk about this. It has a couple of uses. But the first one is to pull stuff from one namespace into another namespace. So as we said, cout and endl are in the std namespace. So if you do using std : cout, that says, hey, I'm going to guarantee you that I don't care about colliding with this. Just pull these two things into the global namespace for me. And after that, you'll be able to use them unqualified. As you can see down here, now we're just saying cout, hello world, endl. And this is fine because we've pulled this stuff into the global namespace, so we don't need the qualifiers. You can also, and I'm only showing you this because you might see it, pull an entire namespace into another namespace. So this statement here, using namespace std, that will pull everything in the std namespace into the global namespace. As you can imagine, the reason that's a bad idea is that it's the entire standard library. There's a ton of stuff in it, and there's a good chance that if you do this, I mean, you probably, especially if you're just learning C++, do not know the name of every single thing in the standard namespace. You're going to eventually write something that collides because there are some fairly common identifiers in here like max and min. And if you're used to max and min working not just as standard functions, you say int max and suddenly you've collided with standard max and things just break. So just don't do this. It'll save you time. It'll lose you more time than you save by figuring out like where you have collisions and why. One other cool thing, and you may know this from Java because Java has system out error as well as out, is there are actually 2 streams on any program that write to the console. One is the standard output stream, and the other is called the standard error stream. The idea being that if you're constructing a pipe and you're piping your output to some file or something, and the program has an error it needs to tell you, it needs a way to tell you that doesn't get eaten up into whatever file you're piping the output to. So in the context of a contest, that's really cool because most judgers only look at the standard output stream. But if you write to the standard error stream, which here is cerr as opposed to cout, then here you're still going to see hello world when you run this program because both of those things go to your console. But the judger is going to ignore this. So this is a great way to put in a bunch of debugging printouts in your code without having to remove them before you submit. Again, I say most judgers. I can't guarantee you that every judger in the world is going to do this. Sparta does this. I know for a fact. And it's one of those things that you should have on your checklist to try in the pre-contest test problems. So before you submit something to get an AC, go ahead and do this. Put some stuff in here like this and see that it gets ignored and you still get an AC. So again, now we're going to talk about compiling a little. This is important to know even if you use an IDE because it is a little more complicated than Java. Pretty much everybody uses G++. On Linux, this is what you're going to get. On Windows, if you're doing contest programming, you're also going to have G++ in some environment like CodeBlocks, even though that's not the Microsoft compiler. On Mac, if you're using a MacBook to do practices, then you'll be using Clang++ by default. That's okay. The command line is pretty much the same, except it's Clang++ instead of G++, and actually I even think there's an alias. The only thing you have to be careful of is we talked about headers earlier. There are a couple of cases where Clang will pull in header files by default that G++ won't. So it's possible that you can write something that works perfectly on your MacBook, and then you submit it, and then it doesn't work because there's a header file missing. Then you have to go figure that out. The suggestion I have there is just be very aware of what you're using in your program and be explicit about what you're pulling in. Even if the local compiler is compiling your program, and it's especially true if you bring in the containers, there's a header called algorithm, which we'll get to later, that you'll want to explicitly pull in. That's the one that normally causes issues. So let's go through this parameter by parameter. So std is C++ 17. There are multiple standard versions of C++ because the language is still evolving, even though it was first introduced in the, I can't remember if it was the late 80s, early 90s. And now there is stuff in modern C++ that was not there. I'll try to call this out when I come across it in the slides. But if you don't put this, then on some versions of G++ stuff will break because it's using a much older version of the standard where some of the stuff didn't exist yet. The reason that this says C++ 17 is that is what World Finals uses. And the presumption is that if World Finals is using this, then everybody else ought to be too. Again, this is a thing that it's good to, if you can't explicitly test this, to at least ask. Most of the stuff that we're going to talk about does not require 17. Most of it is fine all the way back to 11. And it's going to work on any compiler in a judging system. But you can always ask, hey, what compile flags do you guys use? So you know that when you're compiling locally, you're using exactly the same thing the judging machine is using. -O, hello. This is naming the executable that we're going to create. So notice double dash for std, single dash for single character flags. -O means output. And the default here is actually something called a.out, which goes way, way back to Unix in the 70s and has never been changed. So if you don't specify this flag, you're going to get a file called a.out, which makes no sense. So just specify this and make your program be the same thing that the source file is called. This parameter is actually really important, capital O. So lowercase o is output. Uppercase O is optimization. So Java just optimizes. C++ does not. Java can get away with that because it's compiling to its own intermediate language that always knows what it's doing. So it just always optimizes the best it can. C++ actually has multiple levels of optimization. And if you don't do anything here, if you don't put -O, capital O flag at all, you're going to get just base code that's not very optimized at all, and it's going to be slow. So after that, there are various levels of optimization up to 3, 0, 1, 2, and 3 that are successively more and more aggressive levels of optimization. Why are there 3? Well, because there are in some of the optimizations, there are assumptions that the compiler makes about how variables are used and how it can alias things. For the most part, in the code you're going to write, you don't need to worry about that, and you can just use -O3, and that will probably give you the closest to what the judge machine is doing. This can actually be an order of magnitude difference in how fast your code runs. And if you care about having your code run in a close to same amount of time as it's going to run on the judge machine, then you're going to want to do this so you can see if you're close to the bounds. The other reason is, I mean, even if your solution is fast, I mean, having your code run a lot faster means you can iterate a lot faster when you're testing it at the terminal, so you're going to want this anyway. Here, this next line actually shows how to run the program. Unlike Java, C++ compiles down to machine code for whatever platform you're compiling on. And that means that the program you get out is a native program that you can run like any other program without an interpreter. So where you would say Java space hello here to run the hello class, here you just run hello. Unix pathing means that typically you need to preface this with // because hello is in your current directory, and normally your current directory isn't in your path. This isn't true on Windows, but it is true on Mac and Linux. And again, just like Java, the redirection that you use to send your data into your Java program is not a feature of Java. It's actually a feature of the shell, the command shell. So doing redirection with less than to send your test data into that, or if you leave this out, just typing it in from the console works exactly as it does in Java. So I'm not going to spend any time at all on conditional or loop structures, and that's because for the most part these are identical to what you use in Java already. If else, do while for, at least the 3-element version of for, and then switch statements and all of the standard operators. All of these are exactly the same as in C++ as in Java, because C++, all of these things are the same as C, and Java stole all this stuff from C, so all three of those languages, all this stuff is just the same. So now let's talk about the type system. Here are your basic types, which should look very familiar from Java as well. We'll start with char. So char is 1 byte or 1 ASCII character. If you're treating this as a number, and typically you don't do this, there's really no reason to use a type this small in a programming contest problem, but it can either be 120 or negative 128 to 127, or it can be a character, or it can be 0 to 255. But cout will always print this as a character unless you cast it to something else. If you're doing a problem that involves strings, then you'll use char to pull the string apart, because typically things get a lot more complicated when you're talking about non-English languages where you have to step outside ASCII, but most contest problems you can just use char. One gotcha: if you do use this as a type, it is implementation dependent whether char is signed or unsigned. If you want it to be a signed type, say unsigned. You can also say signed char to make it explicitly signed. Int and unsigned int, again, just like Java, these are 32-bit types, which by default are signed. So if you want unsigned, qualify it. If you want 64 bits, then the type is long, 2 words, or unsigned long, 3 words. And float and double are single and double precision floating point types, just as in Java. So a tip: unsigned long is a lot to type, as is long. I mentioned earlier that the using keyword has a couple of uses. This is the other use, and that is to create aliases for types. So if you do using and then some type name you want to create equals some existing type, then this becomes an alias for this type. So after we do this, then anywhere you want this type, you can just say ULL or LL, and this can actually save you a ton of typing. Now we'll talk about conversion rules. These also exist in Java, and I'm pretty sure these rules are the same, but I'm going to go over them here just for completeness, and they can be, especially since a lot of contest problems expect you to step into the realm of 64-bit precision. It's important to know these things. Right now we're going to consider, so we have a 32-bit integer x and a 64-bit integer y. I'm going to note here, if you have a really big constant, it's important to do this to be clear. But you can put LL or ULL. As actually a reason I chose LL and ULL, it's because these are the suffixes that C++ uses to specify constants are 64-bit. So this is a 64-bit constant explicitly, even if you're not assigning it to a 64-bit variable. If you left this off in this case, it would just convert it to 64-bit anyway. Here, and to understand this, we have to talk about overloads a little bit. So C++ allows you to have multiple versions of a function or operator that take different types, and then it does type inference to figure out which version of the overload it's going to use. If that doesn't make any sense, just think of it as how plus or any other arithmetic operator handles different types of operands. So here we have a 32-bit and a 64-bit operand to the plus operator. So the rule in general is that if an operator has a less precise type and a more precise type as operands, it is going to convert the less precise argument into the type of the more precise argument and then do the operation. So what's going to happen here is x is going to become a 64-bit version of 42, and then that is going to be added to the 64-bit version of 100, and that's going to be assigned to z. Here, that's obviously not going to make any difference because even the result here is going to fit in a 32-bit. But this gets important when the result is actually larger than 32 bits. And the next slide will show you why. So say that you have these things as both as integers, 32-bit integers, and then you add them. And now say that these things were very, very close to 2 to the 31. They're very, very close to the limit for an integer of what can be represented in 32 bits. Then you add them and assign them to a long log. The process I just described for how this operator converts its operands, note that these are both 32-bit, so that process is not going to kick in. This is going to add two 32-bit numbers and get a 32-bit number. Then the assignment operator here is going to convert that to a 64-bit integer after the addition is already done. And if you have two very, very large 32-bit integers that are positive that are added, what you're going to get is not a 64-bit positive number. What you're going to get is a 64-bit negative number, which is the overflow of this addition, which is obviously wrong. So the easiest solution for that is, if you know in a contest problem that you're dealing with 64-bit numbers, never declare a 32-bit number. The performance difference it's going to be identical on modern processors because they're all 64-bit processors anyway. And if you just declare everything as 64-bit, then you're never going to run into this truncation problem. Or, and this is just showing another way to get around this, you can actually cast a 32-bit to a 64-bit, and because of the rules, you only need to do this to 1. So now x is a 64-bit, it's being added to a 32-bit, so y is going to be converted to a 64-bit, and again, everything is going to work. But by far the best way to approach this, again, if you know you have a 64-bit problem, just declare all 64-bit variables. Strings, again, are similar to Java strings. So strings are in the standard namespace, and so we have to include a header for them, and the header is just called string. So this is a pattern that is endemic to pretty much all of the standard library. It makes it really easy to know what to include without having to look it up. If you have a class called std : something, where it's string, or it's a container, or it's an algorithm, well, for an algorithm, there's a header called algorithm, because if you use one, you're probably going to use more than one. But for any class like string, or what we'll get to later, collection classes, the header is named the exact same thing that the class is named. And here we're just doing very basic hello, hello, world, world, and then plus, as usual, is concatenation. And you can look online for, if you just search for std : string, you'll find the page with all the different operators you can do. You can do substring, you can do indexing to get individual characters, and all the operations that you would expect on a string. I don't have time to go over all of them, but the reference page does a very good job of that. I'm only showing you this because you might see it in other people's code. I don't recommend anybody go down this path, and I'm going to tell you why. This is C strings being used in C++, which some people still like to do. So the first thing you'll notice the difference is .h here. In C, headers had a file extension of h as opposed to the source extension of C for header file. C++ got rid of that and just names them without an extension. So if you ever see .h, then you'll know that somebody is bringing in a C header file. The other way you can know is that if this is string.h, there's an alias for it called cstring. So if you see include cstring as opposed to just include string, that's the same thing. C strings are just native C arrays, and I'm going to not recommend using native string array, C arrays either, and we'll see why in the next section of the talk. Here we have a string that's 80 characters long. Well, not really. We have an array of characters that's 80 characters long. And we have strings of up to 79 characters long. And the reason for that is, if you notice, there's no information about how long this string is here. String, if we look at the previous slide, you'll notice we never said anywhere in here how long this string was. We just let the string class work it out. And the way the string class deals with this is internally it's got a buffer for the characters, and it's also explicitly storing the length of the string. So here it's storing these characters, and it's also storing the number 7 somewhere to let you know to let it know that this is 7 characters long. But here, that information doesn't exist because this is just a block of memory that's 80 characters, 80 bytes long. So the way C did this was that at the end of the string, there's a null byte, there's a 0 byte. So here there are 7 bytes of data, and this is actually in the compiled constant, and it's also how standard string knows how long the string is when it's turning the string constant into a standard string. There's a null byte here, so it's really HELLO, comma space null that says, hey, you've hit the end of this thing. So strcpy, all it does is copy bytes up until that null, up to and including that null byte into buff. And then strcat is concatenate, and it basically says, hey, look for the null byte that's already there, and then basically do strcpy on the rest of this stuff to put it at the next point in the buffer. So there's a variety of ways to go wrong here. First of all, 80 really means 79. This is the result of a ton of bugs in legacy C code. And if you've ever heard of a buffer overflow exploit, and when people are talking about security, this is one of the things they mean. If you go beyond this 80, in which it's already incredibly easy to make an off by 1 error, then you're basically smashing memory that's near the string. And that will either crash your program, or if you're smart and evil, you can use it to intelligently modify other variables nearby and make the code do something it was never intended to do. And then you get people all freaked out because their PII is all over the network, and they don't know why. The other thing to note is here we as I said, we put a null byte, and here this thing searches for the null byte and then copies this string in. Well, if you're doing this with standard string and the plus operator, it already knows how long this thing is, so it knows where to put world. This thing has to scan and find where to put world. So it's actually doing twice as much scanning through the string as it needs to do to put these two things together. So it's actually less efficient than standard string in that way. Also note, there's no protection here, as I said. These calls, there are modern versions of these, but nobody uses them for the most part, that will say give you the length of the buffer so it can't overrun. But it's pretty easy to see that if you do a bunch of strcopies and strcats and you don't, these are most likely other variables. You have to be really careful to figure out this 80. It's really easy to go over and just crash your program. So for all of those reasons, just don't do this. If you see it, understand what I'm only showing you this so you'll understand what it means. Sorry about that. But yeah, just use standard string. Okay, so compound types. In Java, if you want a compound type, meaning a couple of variables or more held together in a single object, you would use a class for this. In C++, the typical thing is called struct. So all struct is a type that contains other types. or members of other types. So here we're declaring a point, and it has two members, x and y, both of which are integers. Here in main, we're declaring a point, and we're setting x to 1 and y to 2. Just like Java, you can see we're using the dot operator to do this assignment. And then we also use the dot operator here to get the value back so we can print it out. This is all pretty simple. Everything is mutable, so you can change these things wherever you want. But there is a major thing here that you have to think about, especially if you're a Java programmer. And that is Java, if you create a class and it's just a plain old data class and it's got an integer x and an integer y, these things are nicely going to be 0 for you. That is not true in C++. In C++, if you just do what we did back here, at this point, before we assign to x and y, these are not 0, they are garbage. They're whatever happened to be in the memory that the compiler decided to use to store point in. So you either have to be very careful to assign everything a value, or you have to have a default constructor if you're going to expect the value or the behavior that you get out of Java for free. This goes way, way back to C. This was done for performance reasons. In modern language design, it's a horrible idea, but they still can't change this for reasons of backward compatibility. So this is just a very simple constructor which shows you the format. As in Java, the name of the constructor is exactly the same as the name of the class or the struct. And you define it. So it's interesting. Here you actually define the methods in C++ outside. You can define them in here as you do in Java. Typically, though, people declare them outside, and that's typically because this part lives in the header file. You would, if your program was any size, which yours won't be, you would put this in a header file so other people could use it, or other parts of your program and other source files could use it. And then you would have to carry around this declaration all over the place. So point : point says just like a namespace, but instead we're qualifying with the name of the struct, that this point method now instead of function is a member of this point class or struct. And this thing is called an initializer list. It's pretty easy, : after the declaration, variable name, and then parentheses this initial value. This can be cumbersome in some ways for simple variables like ints. This is a very, very terse, easy to type way to do this. For more cumbersome things, like say you actually had to make method calls on these to get them, say like these were collections and you wanted to set them to a size, then you would put that in the body of the constructor. But if you're moving from Java to C++, this is probably one of the most common things people do to generate bugs, is not realize or out of habit think about the fact that things do not have reasonable values in structs when you just create them. Another difference between C++ and Java. So in Java, if you create an object from a class and then you pass that object into a function, you aren't actually passing the entire object around. You're passing what's called a reference. It's basically the address of that object, and that is way more efficient to pass around than a large object because you don't have to copy it. In C++, you have to do this explicitly, and the way you do this is with something called a reference. So here, we're just going to start with doing this on an integer, even though an integer type actually will be copied, and it doesn't matter because an integer is the same size as a pointer, so it's just as efficient. In general, by the way, I mean, if you have like a point, which is 2 integers or a small struct, it's fine to just pass those things around without using a reference, but for anything bigger than that, you want to start using references. So here, the ampersand here means I want a reference here, and then ref is the name of the variable. Now, after the statement, ref is an alias for ants. You can think of ref and ants as the same variable at this point, as they both refer to the exact same piece of memory where this 42 is stored. So if I do ref plus equals 4, what I'm really doing here is ants plus equals 4. So here I'm going to get 46 because I've just really incremented this by 4. So I mentioned before avoiding pointers, and one of the key differences between pointers and refs is pointers can be initialized to something called null, which your references in Java actually can also be set to null. But that is a huge source of bugs because if you dereference null, you just immediately crash. So references were one of C++'s answers to that in C. You have to initialize a reference to something. So here, this is a compile error because we have this reference oops, but it doesn't refer to anything, and references always must be initialized to something. So yeah, you just can't do this. You can, however, have a constant reference. And what this means is this is still an alias for ants, but we could not do cref plus equals 4 because we've guaranteed by saying const here to the compiler, hey, we're not ever going to change ants through this reference. Why that's useful we'll see later on when we get to function calls. And that's the end of part 1. Come back soon for part 2 where we'll talk about functions and collections.